All right, second page here. Exponential growth versus exponential decay. And we're going to look at the official formulas that we give to model these exponential growths and exponential decays. So these two formulas, as they were, are pretty much the standard form of the exponential shown on the previous page, which was, f of x equals a times b to the power of x. But we've just done two things. We have replaced the x with a t, because t can stand for time, and for modeling real life things, the exponent's often time. So same kind of thing. And then the b, it's been changed to be either 1 plus an r or 1 minus an r. But the key thing is to realize that this expression, 1 plus or 1 minus r, that ultimately is a base. This is an exponential growth model. So I'll tell you right now, whatever the result of 1 plus r is, it's going to end up being a number bigger than 1. This is an exponential decay model, so whatever 1 minus r is, it's going to be a number less than 1. That makes sense, right? Especially if r is some number like a percentage rate, like, I don't know, say 20% would be 0.2, 1 plus 0.2 would be greater than 1, whereas 1 minus 0.2 would be 0.8, that's less than 1. So just logically that should make sense. Let's look at an example then. So the value of a car in thousands of dollars can be approximated by this model. 25, that's our A, 0.9. So this is the result of a 1 minus an r, and we got 0.9. So I wonder what r is, where t is the number of years since the car was new. Tell whether the model represents exponential growth or exponential decay. Well, this is easy. Again, if that b value is less than 1, but of course greater than 0, it's decay. I mean, the car value goes down over time. Mostly shouldn't be investing in cars. Their value doesn't go up. Identify the annual percentage increase or decrease, we obviously have a decrease here, in the value of the car. Okay, so here's where we just do a little bit of math, but again, you could probably have figured this out. If this is the model for decay, and this is what we actually have, again, I can see clearly, okay, so the A is that 25, the T is just the time T, but the 1 minus R, that 1 minus R, it somehow ended up being 0.9, or 0.90. Can you solve for R in this equation? It's like a 2 or 3 step equation, minus 1 for both sides divided by the negative, but hopefully you can just see, what do I got to minus from 1 to get it to be 0.9? R would have to be 0.1, or in percentages, with the decimal point over 2 spots, that's 10%. So the car is going down in value 10% each year. Now, let's use this information, not that we need it to identify this, but we can just use the model to estimate the value of the car, when the value of the car will be 9,600. And so this is where they're giving us the y, and we need to find the t. So one thing that's tricky is this y is in thousands of dollars. So I do believe that we're not going to write 9,600 equals 25.9t. We're going to write 9.6, because that's $9.6 thousand equals 25 times 0.90 to the t. Now, in theory, we can just solve this. The other option is we can just plug in a bunch of values for t and see which one actually works out. There's a thing we'll learn in a later section, which is like the official tool we'll use to do this. But for now, let's just kind of use our calculator and say, all right, so, algebraically, I might divide both sides by 25. And then, do some stuff. But let's just be kind of blunt about this and just say, okay, let's do 25 times 0.9 and raise that to the power of, let's just pick a year. How about we say 1 year? And so this is going to give us the value of the car, again, in thousands of dollars. So now it's $22,000. That's not 9.6. So I could just go back and change this to, change this to 2. Get my calculator just say everything is fractions first, but 20. Okay, that's clearly not it. Okay, let's go a little harder. Let's I don't know, 5. Okay, 14. That's closer. But we gotta go longer. 6, 13. All right, let me just jump up. 8, 10. Oh, we're getting closer. 9, Oh, look at that. At 9 years, we're at 9.6855. Now, if we want it to be down a little bit more, it's going to occur sometime between the 9th and the 10th year, I would imagine. We can verify this and change this to 10. But yeah, at 10, we're down to 8. So our time is, we're going to put, it's around the, from year 9 to year 10. So somewhere in that, going from 9th to 10th year, it's going to drop down to 9,600. Now, that's not very precise, by the way. Maybe you can mess around with decimals and figure out a closer thing. But one of the things you'll learn later, and say spoiler, it's called a logarithm, that'll teach you how to find this exactly. Let's do another example of the same kind of thing. So in the year 2000, the population of the city was 1.2 million. During the next 8 years, the population increased by 2.5% each year. So this is an exponential growth model. Now, they've not given us the model, so they want us to write that model. So we'll just reference this and kind of fill in what we've been given. So one thing that may have been most clear is this, especially in the last problem, that 25, that's $25,000. That was the initial value of the car. So A kind of represents that initial value. And that's actually the official term for it. I can't remember if I mentioned that already. So the 1.2 million, that's going to be our A. Our A is 1.2. I was going to put mil. We understand that's 1.2 million. The rate is 2.5%. So I would not blame you if you said R is 2.5. The issue is that's a percent, and in math we work with decimals, so we got to move that decimal place over 2 spots to actually write it. So R won't be 2.5, it'll be 0.025. Actually, wait, did I get it right? Hang on. Yes, I did. Yeah, that's right. So that's the actual R value. And then that's all you need. Let's just plug this into, again, this standard form, and what we'll have is and I can write this as the let me go fancy here, the population with respect to time, this could be the y, but the population with respect to time is going to be 1.2 times 1 plus 0.025 to the t. So that is the model, which will give us the population t years after 2000 in this case. And now they want us to use it to estimate the city's population in 2008. So this is t years after 2000. So we're not going to plug in 2008 to t. We're going to plug in the difference between 2008 to t, which is 8. So again, you just type that into a calculator. 1.2, parenthesis, 1 plus 0.025, which, by the way, that's just going to be 1.025. Just going to type in 1.025 again. And then, yeah, that's raised to the 8. And we'll see. So it's going to be 1.46 million. I'll just write this down. Just write 1.2 times 1.025 to the 8 equals about 1.46 million. And I realize this might be confusing because I just did that problem here. They also want us to estimate the year when the population would be 1.25 million. So when is it going to be, when is the output going to be 1.25? It's the similar kind of question to the car value one, where we're now trying to find the time. What time do I got to set this to be so it's 1.25? And I'll tell you this, it's not going to be higher than 8 because 8 obviously grew past 1.25, so it's a much smaller number. And again, we could just play around with the numbers. We could say, well, let's shoot, 1.2 to 1.5, that should be too much, maybe 2. Oh, look at that, that's already 1.26. So it looks like it probably would grow in about 1 year, somewhere probably between 1 year and 2 years. Yeah, 1.23, so it's going to go over to 1.5 from years 1 to years 2. So t equals, or is about 1 to 2. Or I should say between 2001 to 2002, somewhere in that range, it became 1.25 million. Last example, and by God, this is the trickiest one. So the amount Y in grams of a radioactive isotope remaining after T days is given by this formula, where A is the initial amount in grams. What percent of the isotope decays each day. Now you might be like, well, is it just 0.5? Because 1 minus 0.5, and that would be right if it weren't for the fact that this is not raised to the power of just t, it's raised to the power of t over 13. What's going on there? And this is how people do a thing called half-life. It's just another way to represent exponential decay. But essentially, if t is the time in days, if you divide t by 13, that means t will go up 1 every 13 days. So 13 days later, t is at 1. 26 days later, which is another 13, t will be 2. So it basically allows you to have the t increment by sets of 13, and every time that power goes up by 1, you are raising 0.5 to that power, which 0.5 of anything that's basically times it by half is taking half of it. So this is a way of saying half of the substance will be gone after 13 days. In another 13 days, half of that will be gone. In another 13 days, half of that will be gone. And that's how a lot of these radioactive isotopes decay. They will keep falling in the amount that's left. You know, theoretically, they never completely dissolve because you just keep taking half of a smaller and smaller number, but they decay very quickly into almost nothing. Well, not always very quickly. In this case, 13-day half-life isn't too bad. Some things have a much longer half-life. But at any rate, here's our issue. We want to write the formula, you know, y equals a times, and this is radioactive decay, 1 minus r to the t. We want this formula, but we are given this formula. So I got to reconcile these exponents before I can reconcile the internals. And this is where we use a rule about powers, and that is t over 13, we could think of that as being t times 1 over 13. So we have 0.5 to the power of t times 1 over 13. And then further from this, if you have the product of two powers, you can use the rule when you have a power to a power in reverse. It's quite tricky, but basically we could write this as 0.5 to the 1 over 13, and then that is raised to the power of t. If this is confusing, I'll just remind you that, again, if you have x raised to the power of, say, a, put that parenthesis in the wrong spot, and then raise that to the power of b. So if you have something, if you have a thing raised to a power and you raise that to a power, that's equal to x to the a times b. This is power to a power rule. Well, we're kind of using that in reverse. If we have the product of two powers, which technically a fraction here we thought of as a product, then we could represent this as 0.5 to the power of 1 over 13 raised to the power of t. Why are we going to do that? Well, I could evaluate this. Now, you were probably going, oh my God, what is that? Well, we have a calculator for that. So 0.5 raised to the power of fraction 1 over 13. And we get a very ugly decimal, but it is now, this decimal is now whatever 1 minus r was. So we get 0.948 to the power of t. So 1 minus r equaled 0.948. And again, that's an easy solve. It's like a two-step equation. I'm basically asking, what did you subtract from 1 to get 0.94? And it's going to be a small number. R will be something like, here, I'll do it fast. It will be about 0.5. I'll round up to 2. Let's see. 0.052. Which, as the last thing they want is, so what's the percent? You'd actually convert this back to a percent. So the percent in the end is going to be about 5.2%. Very tricky, but there's one like this on one of the check for understanding. So use this as a template for how to do it, particularly with this trick right here.